Hello and welcome to my presentation. My name is Syed Asad Alam and I'm here to represent my work in progress paper titled Beyond Base 2 Logarithmic Number Systems. I'm a postdoc research fellow at Corias Research Group at the School of Computer Science and Statistics in Trinity College Dublin, the University of Dublin. This paper has been co-authored by my supervisor Professor David Drake, and we both are members of LERO, the Irish Software Research Centre. I have divided my presentation into 4 parts. So first I'll talk about the motivating factors led to the study, the contributions of this work, experimental evaluation to show the results, and the concluding points. So the first factor that motivated or led to the study was that we were looking for a number system that can quantize or represent floating point number system with reduced word lengths to target embedded devices, and a number system that has a non-uniform distribution and which can represent smaller numbers more accurately at the expense of representing larger numbers less accurately. And this is because if we look at the parameters, the weights and the feature maps of a neural network, the values of the data is concentrated or lie within a very small range of small numbers. So we wanted to have a number system that maps to the distribution of the parameters of a neural network as against a uniformly distributed number system like a fixed point number system. This eventually led to a more generic study of logarithmic number system. So why LNS? Well, first of all, LNS has a non-uniform distribution that maps well to the feature maps, the weights, the biases of a neural network, and furthermore, multiplication in LNS reduces to addition, lowering its implementation cost. And also, if you multiply two numbers in, let's say, a fixed point number system, to accurately represent the result, the required word length of the product is more than the input numbers. So you need to round it down to the original word length, and then obviously you run rounding issues and accuracy issues and so on. This will not happen if for multiplication you only perform an addition. Yes, there are some problems with LNS like addition and subtraction, and I'll get back to that later on. Why 8-bit? Well, we were targeting resource constrained embedded devices, and the lower the word length, the better it is, because that will reduce the memory and the throughput requirements of the application. And the number format that we have used for our data is 1 sign bit, 4 integer bits, and 3 fractional bits, which correspond to the number format for an 8-bit floating point number, also known as millifloat, which has 4 bits for exponent and 3 bits for mantissa. So, talking about contributions, the main contribution of our work is the analysis of other bases other than base 2 in LNS with 8-bit data in terms of 2 factors. First, how well can we represent an 8-bit mini float with various bases in LNS and not just base 2, and what are the errors when we are trying to approximate the addition and subtraction LNS with various bases. Why do we approximate these 2 operations? I'll come back to that later. But the important thing is here, how do we define it? We define both of these factors in terms of an error, and the definition of error is we use the average relative error. The formula is given here. So we find the relative error and then we take the average of it, and then the average relative error is represented as a percentage of 1 ULP, or the unit of least precision, which basically, and what is ULP? One ULP is the smallest number that one can represent in a given number system, and in the case of LNS, the formulation of ULP is shown here in the slide. The first error that we analyze is the representation error, and we define it as the relative error introduced when representing or quantizing an 8-bit mini float number into LNS. And what does that mean? So for that, we have this figure here. Here in the figure, we have 2 figures for 2 different bases. The crosses here are the floating point numbers, and the asterisks or stars here are the numbers in LNS for different bases. And quantizing floating point or representing floating point means that instead of this number, we use this number. We represent this floating point number with this LNS number. And as you can see in these two figures here, there will be a certain error when we will represent each floating point number. From that error, we will calculate the relative error and take the average of it and represent it as a percentage of 1 ULP. And what are we targeting? Well, different bases will represent the floating point number with different error, and we are trying to find out the base that gives us the least or the smallest representation error. However, there is one thing important. The important thing to consider here is that the range of numbers for various bases in LNS is very different from the range of a floating point number. So, for example, for an LNS number system based on base root 2, the range of numbers is only plus minus 15, while the range of a mini float is around plus minus 240. So, if you are trying to represent a floating point number with a smaller base, the smaller bases with its reduced range will obviously will have more representation error, and the higher or the base, the lower will be the error. So, in order that both of the number systems that we are looking have similar range, we scale our LNS numbers by a scaling factor, so that the floating point number and the LNS number in all bases have a similar range. So, we multiply each number in LNS by a scaling factor, which is the ratio of the maximum floating point number to the maximum LNS number in that particular base. So, we introduce scaling before quantization. The second error that we analyze is the arithmetic error, and we define it as the relative error introduced when approximating the addition and subtraction operation in LNS. Why do we need to approximate these two operations? Because LNS is not closed under addition. It means that we cannot represent addition or subtraction, for that matter, accurately or exactly in LNS. This means for example, let this be a set of numbers in LNS for base 2. So, you have, if the exponent is only integers, so the numbers you will have in LNS set would be 1, 2, 4, 8, 16. So, if for example you add 1 and 2, the output will be 3, but 3 is not in the set. So, you cannot represent 3 accurately, so you have to approximate it. The way we approximate is by using this formulation, and the key element of this operation is this function phi of x, which consists of two functions, phi plus, which we refer to as the addition function, and phi minus, which we refer to as the subtraction function, and it's basically finding the log to the particular base of this factor. There are various ways to calculate this factor, but for shorter word lengths, the appropriate way is using a table with pre-computed values to compute this operation. So, we use a table with 8-bit values within it. So, looking at the experimental evaluation, here we show the percentage average relative error for when we are representing a floating point number using various bases in the LNS number system. And in the first graph here, we show the error for various bases when the numbers in LNS are unscaled, and here on the right hand side we show the error when the LNS numbers are scaled. And we can see here that for the unscaled data, the higher the base, the lower the error, but when we scale it, we see a minimum point here much further away from base 2, and we get a point here which gives us the least representation error. What are these two values? For unscaled it's 1.984, and for scale is 1.851. The second evaluation is of the arithmetic error, and you can see here the arithmetic error for various I haven't shown all, but for some various interesting bases, the arithmetic error is concentrated within a small range, and that's around a quarter of a ULP, and that is expected because when you quantize something, the maximum error is around 0.5 of ULP. So, the average error would be around 0.25. Although we have got some bases which produce the smaller of all the results, but there is no global optimum, and for arithmetic error, the error in the two tables for various bases are similar. So, we will have to strongly consider the representation error, where here this error is for unscaled data and this is for scaled data, and we can see here that the base of 1.851 gives a significantly better representation error or significantly lower representation error as compared to base 2 or other bases, and the error that it gives for arithmetic error is not a lot worse than the best cases here. So, but 1.851 is sort of a compromise, or for our case it is a good base. The base of 1.741 is the base that gives the lowest representation error when we constrain the the values to just plus minus 1 and without scaling. So why is it important? A number of applications like FIR filters or IR filters in DSP have their values that are constrained within this range. So to conclude, selecting an appropriate base can lead to a few lower errors for low precision values. For higher precision values, we did some studies, and the difference in errors were not that great. The difference for shorter word length is very significant. So we need to analyze our application, our data, to find which base gives the lowest error, because the selection of base and the scaling factor also is dependent on the total word length, the range of numbers that we are dealing with, and the application. And for our case with 8-bit numbers within the range that we have defined, 1.851 is the best compromise. So with this I conclude my presentation, but before I finish off, I would like to acknowledge my the funding agencies for my postdoc. The first is SFI, the Science Foundation Ireland. The other is European Union's Horizon 2020 program through the Marie Curie Scholarship grant agreement number 754489. Thank you very much. Bye.